So in addition to free radicals reacting with sigma bond hydrogens, allylic hydrogens, benzylic hydrogens, and we said that for these we are using a chlorine in presence of light or bromine in presence of light or MBS. Chlorine, we said that it is very reactive. This is why you get a lot of products, and the bromine is targets a specific hydrogens. It targets the allylic, the benzylic, and the tertiary hydrogen. And they're together with the MBS. So in addition to that, free radicals also can react with pi bonds. For these types of reactions, we're going to consider only one reagent. So we're going to consider the reaction of HBr in presence of peroxide and light. We've talked about this reaction in Organic 1 whenever we were discussing alkene reactions. So we're only going to consider HBr. We're not going to consider HCl in there. HI and HF will not have a reaction. So it's just the HBr that will do the reaction in this case. Okay. The reaction is going to follow anti-Markov-Likov, where hydrogen will be added to the most substituted carbon, and the bromine is going to be added to the least substituted carbon. Notice that in these reactions, I am not starting with Br2 or Cl2. I'm only starting with HBr, and this is the only reaction, free radical reaction, that we're going to consider with pi bonds. So let's go ahead and have an example. I am reacting this alkene with HBr in presence of peroxide and light. Peroxide is going to be cleaved by light into free radicals, and that is going to be your initiation step. So with initiation, again with these reactions, the moment you see peroxide, the moment you see light, you know that you are working with a free radical reaction. Free radical reactions do not involve a carbocation. It's just the free radicals. Carbocations, they do not exist here. Carbanions, they don't exist. It's only free radicals. So in the initiation, you start with the peroxide, and we said that the sigma bond that that is between the two electronegative elements, this is the weakest bond. So when this one is exposed to light, then it's going to be it's going to break, and it's going to break by a homolytic cleavage, and each of the oxygens is going to carry a free radical. Now this is going to start the reaction by reacting with HBr. We are still in the initiation. So the whole idea in the initiation is to generate a free radical. The free radical that is generated is from the peroxide. So the HBr is not going to react with light and get cleaved, because here I do have the sigma bond that is weaker than the bond between the hydrogen and the bromine. So this one is going to be more reactive. It's going to start by reacting first. It's going to cleave under light into free radicals. Remember what we said at the beginning, free radicals, they take hydrogens. So over here, the free radical is going to come and take the hydrogen, and bromine is going to form a free radical. So you're going to end up getting water plus the bromine free radical in there. This bromine free radical is the one that is going to react with the alkene, with the double bond. So here I did create a bromine free radical, and that free radical is going to come now and react by the two steps of propagation with the double bond of the alkene. Now we're going to do the same thing as we did in every single free radical reaction. Not all the HBr is going to be cleaved by the peroxide radical. Some of them are going to remain unreacted. So we're going to write over here plus unreacted HBr. And this unreacted HBr we're going to use in the second step of the propagation. Okay, so now we're going to go ahead and do propagation. Propagation is 2 steps. So the first propagation step is going to start by the reaction of the alkene with the bromine free radical. Now, this reaction over here is going to be on the double bond. So the bromine free radical will react to the double bond. It's not going to react with any of the allylic hydrogens in there. The reason why, because here I am adding HBr. I am adding a hydrogen to one carbon, and I am adding a bromine to the other carbon by anti-Markovnikov. So the mechanism is going to go by the formation of radicals only. So you're not going to form any carbocations in here. No C plus, no C minus. No carbocations, no carbanions. So the double bond is going to start opening up and grabbing this radical on the bromine. And then the electron of the pi bond is going to come and add to the most substituted carbon, because our target here to form the most stable free radical. If you form the free radical in here, it's going to be a primary radical. If you form it here, it's going to be a tertiary one. So this is why we always say that the bromine adds to the less substituted carbon, because in the propagation, you start your reaction by the bromine. And you want your bromine to add to the less substituted carbon so that you can form your free radical on the most substituted carbon. So now I'm no longer going to have a double bond because this is an addition reaction. I am breaking the pi bond using one electron to couple with the other electron of the bromine. And now I made a sigma bond with the bromine over here. And the other carbon is going to be a free radical. That is going to be a tertiary radical, so it's going to be stable. This is going to be the first step of the propagation. The second step of the propagation, we're going to use the unreacted HBr, as we always do. So now we're going to have our intermediate, and we're going to react it with the unreacted HBr in this case. And remember, free radicals, they take hydrogens. Okay, free radicals, they take hydrogens. So here I do have an available hydrogen in there. So what's going to happen now is that the free radical here is going to come. It's going to couple with this sigma bond in there, an electron to make a bond between the carbon and the hydrogen. And the other bond is going to create a free radical so that the reaction keep going on and on until we stop the reaction. So what I did over here is I added to the double bond. I didn't add to the allylic carbon, guys. I added to the double bond. So over here, I am adding to the double bond. There is no rearrangement whatsoever in free radicals. So whatever the position of the double bond is, this is where you're going to add. Hydrogen is going to add to the most substituted carbon, and the bromine is going to add to the less substituted carbon in there. So that is going to be my product, plus, of course, the Br free radical in there. So this is why I need to do termination at the end. And with the termination, just to grab all the radicals in there. What I have here is HBr. So I have a hydrogen free radical plus a bromine free radical that is going to make HBr. I also have a my free radical that I made. I can react this with a bromine free radical. And I'm going to end up getting a dibromination. And this is one of the byproducts in the reaction. I can also have the two bromine radicals reacting with each other. and forming a Br2. I can also have, you don't have to write them all, but I'm just listing the possibilities here. I can do both of my free radicals in there. So I can react both of the free radicals together. And I'm going to end up forming my dihalide product. So here you go. So you have a bromine over here. And this is what we are doing. We're making a bond between this carbon over here and this carbon over here. So just go ahead and draw them as you see them. Here you go. So that is going to be a bromine, and this is the bond over there. And this is again another byproduct. So these are the possibilities for termination. Again, you don't have to write them all, just pick 3 and write those out. There are more examples of these reactions in the problem sets. Please practice them. Just a side note that benzene is a conjugated system. And with benzene, you have these double bonds. They are connected together because you have 6 p orbitals in there. So you cannot break one without breaking the other. So if I have benzene and I want to do any of the free radical reactions that we've been talking about. So if I want to do bromine in presence of light, if I want to do MBS in presence of light, or if I want to do an addition to the double bond, which is HBr in presence of peroxide and light, there will be no reaction. And the reason there will be no reaction, because I cannot first break the double bond. So this is why HBr cannot happen, addition of HBr cannot happen in here. Second in there, I cannot take out the vinylic hydrogen because we've talked about vinylic hydrogens and we said that these are strong bonds because they create a less stable free radical. So the bromine free radicals from these two reactions cannot come and grab an sp2, a hydrogen that is connected to an sp2 carbon in there because this bond is strong. So this is why any of the free radical reactions will have no reaction with the benzene. The double bonds of the benzene cannot be broken this way. There are special conditions for breaking the double bonds of the benzene and taking that sp2 hydrogen. This is not one of them. The last section is polymerization. And polymerization is a process that you use in order to make a polymer. Now, polymers, they are large molecules, and these molecules, they are made up of repeating units. The repeating units, we call them monomers. Repeating units need to have a functional group in there, and the functional group needs to have a degree of unsaturation because after all, the pi bond is going to open up to create a new sigma bond to link the monomers together. So let's go ahead and consider this example where we have X number of ethylene monomers. Ethylene is the IUPAC name. The common name is vinyl. So here I'm having vinyl monomers and I want to link them together. So to link them together, you need to have your monomer having a degree of unsaturation, a pi bond, so that that pi bond is going to open up and you're going to use the 2 electrons of the pi bond to create a new bond. And the new bond is going to be between this carbon over here and this carbon over there. So you're going to form a new sigma bond, and these new sigma bonds that you're going to be forming, those are going to link the monomers together. So you're going to end up having a long polymer chain. That polymer chain, normally, we represent it in its abbreviated form. And the abbreviated form, you take one monomer unit, and you draw 2 sigma bonds along that one monomer unit. You put the parentheses in there and you put to the end. This means that this is linked n times. And then you name your polymer. To name the polymer, just name the monomer and add poly at the beginning. So that is going to be polyethylene. So whenever you see a polymer chain, all what you need to do is always go ahead to the end of the polymer chain and look at the last carbon that you see, okay? Because this bond over here is a sigma bond that is made up by opening of the pi bond. So you look at the last carbon that you see and figure out the repeating unit. So here what is repeating are two carbons. So I have two carbons in here. These are connected by a new bond. Two carbons connected by a new bond. So the repeating unit is the two carbons. So you take the two carbons whenever you want to draw the representation of the polymer or the repeating unit of the polymer. You take the two carbons, you add one bond to this side, you add another bond to this side, and you draw the parentheses and you put it to the end. So let's go ahead and have this example. We want to figure out the repeating unit. So as I said, the first thing that you do is you look at the last carbon in there and figure out what is repeating. So over here, see what's repeating. It's these two carbons and the CN. It's these two carbons and the CN. So this is going to be your repeating unit in this case. So now you take that repeating unit in there. This is the cyanide. And then you draw a bond here and you draw a bond in here. And you put those in parentheses, and that is going to be your polymer representation of the polymer chain. This is going to be the repeating unit. Okay, now if I ask you, go ahead and get the monomer for this polymer, you take the repeating unit, which is the carbon and the cyanide, and you place a double bond in there. Because we know that this double bond is going to open up and create a new bond. And then you have another monomer in there of the same kind that is going to have its double bond and it's going to open up and create a new bond. So this is how you get the long polymer chain. Now, to name this polymer in here, we're going to name it based on the monomer. So the monomer here is vinyl cyanide. Vinyl cyanide is the IUPAC name. The common name is ethylene cyanide. This is a polymer resin. So to name this polymer now, all what you need to do is just put the word poly in front of either the vinyl cyanide or the ethylene cyanide. Because the vinyl cyanide is two words, you can put parentheses in here.